Okay, let's have a short discussion on the idea of distribution shapes, right? Because once we've gone through and we've been able to take our data, organize it, whether it's quantitative or qualitative data, quantitative data is what we're really talking about with distribution shapes. But these distribution shapes tell us something about what the data is like. So a distribution of a data set is whether we take a table, a graph, or there's some formula that provides values for the observations and how often they occur. When we talk about the distribution of a data set, we're talking about how that's distributed, and there are different ways that we classify those kinds of distributions. The way you want to picture what's going on is this. Let's say that we get a histogram that represents our data. What we do is we join the middles or some point within each of those bars of our histogram, and we simulate it with a smooth curve. So when you look at each of these smooth curves in the following slides, we're not talking about smooth curved data. We're talking about histograms, and we're using these distribution, I guess, lines or these curves to represent various heights of bars, right? So we're still talking about histograms and bar graphs, right? We're just interested now in what sort of general shape do they take. And by the way, this general shape, this is a nice symmetrical shape, right? Look at that. That looks almost like a bell. And that's a very famous curve in statistics, one that comes up a lot. We'll talk about that in Chapter 6. But there's different shapes that we can take. If we got a histogram and we had only one place in our data where we had a highest value, right? We call that unimodal. So there's one mode. A mode is the word that we use for most frequently occurring piece of data. So unimodal means one mode. Bimodal means that we have two modes, right? So there's more than one mode. We can have multimodal data, right? Data with lots of high points, right? In our last slide, this was unimodal data, right? This is a one mode, one highest class, one largest group. Now, if it is unimodal, there are different shapes that we can talk about there. Bell-shaped, right? Like our first curve that we talked about is the kind of curve where we have this nice, even, symmetric distribution about the middle, right? And it looks a little bit like a bell. But the data could be triangular, right? If we describe a data distribution and we say it's a triangular distribution, then the data evenly goes down on both sides like sides of a triangle. A uniform data set would be one in which the data, as we go from left to right, stays uniformly about the same size. Yeah, there might be a mode or a low point, but on average, we never really quite leave those bars pretty much being the same size. So these are called symmetric distributions, and we're interested in finding symmetric distributions if we can get them, because they're very useful to us. Now, if there are distributions that are not symmetric, well, then we sometimes say they have a skew. So right skewed data is data where we have, well, lots of small number data right down here, but we might find these outliers, very high numbers as compared to the data up here. And when that's the case, right, we get this big long tail, we call that a right skew. So data that is skewed to the right is data that has this big long tail worth of data distribution off to the right. Left skewed, of course, is just the opposite of that. We'd skew to the left, where we have that big long tail worth of data there. Occasionally we'll have data that we call reverse J-shaped. So what is a reverse J-shape, what we're talking about is data that will have the highest amount at one end and then just gradually decrease down to the other. So this sort of J is formed right here. We call that a reverse J-shaped distribution. It's a little bit like remembering, I guess, aircraft and classifying them according to their shapes, right? If we know something about these distribution shapes, they can help us find out something. So, for example, here's a relative frequency for a histogram of household size and the number of people who live in a household. And we see that, well, this is definitely right skewed data. Why? Well, if we look at our histogram right here, it's unimodal, right? the curve that we could draw in here has one mode, and that's above 2 people in a household. The curve peaks at 2, comes up from 1, peaks at 2, and then goes down gradually towards 7. And there's some households that have 6 or 7 people, but they're outliers as compared to this smaller number where you've got the higher values, right, the higher frequencies. And so we call this right skewed. So this is unimodal right skewed shape. All right. Now, population and data, when we differ when we look at these distributions as to whether we're talking about a population, which is the entire group of things, the entire population we're talking about, or a sample, the values of the sample data. And the population distribution, we sometimes call that a population distribution, or we use the words distribution of the variable. When you see those words, they're talking about the entire population. This is as opposed to the sample distribution, in which we're just talking about the sample. Here's an example of some population distributions of 6 samples, right? Here's the population. So here's what that population distribution looks like. And if we were to look at the sample distributions, sometimes there's slightly different frequencies, but you look at that shape, and very often the shape of your sample distributions overall seem to reflect what happens with the population distribution. And that's an important fact that we'll take advantage of later, that says that, well, if we do have a sample distribution, very often that sample distribution, while not being exactly the same as the population distribution, is usually a really good reflection of the population itself, provided that we've done our job sampling to represent that population correctly. Population sample, random samples, right? For a simple random sample, the sample distribution approximates the population distribution, as we saw in our last slide right here. Each of these sample distributions looked a bit like the population. And the larger the sample size, the better the approximation tends to be. Well, that would seem to make sense. That's almost common sense and doesn't have to be stated, right? If we have a large size sample, let's say we have a population of 1 million people, if we sampled 100 people, and if we sampled 10,000 people, right, the 10,000 sample would certainly be a much better approximation to the population than the sample of a size 100. So we'll talk about misleading graphs in the next section.